Previously on MasterChemist Australia, our amateur chemists have been challenged with inorganic synthesis, but Ada, Marcus and Tom faltered under the pressure. Tonight, one contestant is about to go home. In MasterChemist, there is no time to play it safe. To keep themselves in the competition, they must follow the method closely, and most importantly, understand the chemistry.
In this MasterChemist pressure test, you'll be synthesizing silver nanoparticles. Nanoparticles of silver are between 1 and 100 nanometers in size. Their color is dependent on the shape and size of your nanoparticles. You can find them in biosensors, antibacterial chemicals, and nanowires. But what are you waiting for? Your time starts now!
Whoa, it turned blue. I remember Veronica telling me to use silver nitrate as a source of silver cations. Then sodium borohydride, which acts as the reducing agent to reduce Ag plus cation to Ag. Then hydrogen peroxide, which acts as an oxidant in the reaction, since when reduction occurs, oxidation must also occur. Then sodium citrate, since it provides an alkaline environment which promotes nanoparticle formation and allows other particles to act as reductants. It can act as a capping agent to slow and eventually stop the growth of nanoparticles, keeping them in their nanoparticle size. Finally, potassium bromide, where the bromine minus ion is known to strongly bind to the surface of silver, forming silver bromide that arrests the growth of the silver surface.
I think I added too much potassium bromide, since bromide anions can control the growth of the crystal and change the size and shape. Now my crystal will be of a different color. This is because light is an electromagnetic field. The electric field of the light interacts with the electrons of the silver nanoparticle. They exhibit surface plasmon resonance, where plasmon is a quantum of electron oscillation. The resonance is from a collective periodic oscillation of the conduction band electrons, and when the frequency of the incident wave is equal to the bulk metal plasma frequency, light is absorbed. The color is due to the wavelength absorbed and changes with the size and shape, and thus KBR added.
I can't believe I synthesized bulk silver using a displacement reaction and not nanoparticles. Bulk metals interact with light via reflection, as light, an electromagnetic wave, causes the electrons to oscillate. These oscillations produce another electromagnetic wave, which causes reflection, whereas silver nanoparticles absorb some of this incident light. Time's up! We'll now use dynamic light scattering to measure the diameters of your silver nanoparticles. Small particles like silver nanoparticles in suspension undergo random thermal motion. This scatters the light, which will allow particle size to be determined. Analysis of the variations yields a diffusion coefficient, and we will use this to find the hydrodynamic radius. From this, we'll determine who has synthesized the correct nanoparticles. Tom, no DLS data could be determined because you synthesized bulk silver. Marcus, you used 10 microliters of KBR and you had an 81.9% particles at a diameter of 35.8 nanometers, and so you have the correct nanoparticle size and color. Ada, you've used 25 microliters of KBR, and you had 89.3% of particles at 43.3 nanometers, which is the incorrect size and color. However, Tom, I'm sorry to say, you're eliminated.
I'm sorry.